Beyond what we can see, beyond what we can imagine, lies a universe that stretches farther than light can travel. Every star, every galaxy, every glowing cloud of cosmic dust is a fragment of a story billions of years in the making. We have looked up for centuries, wondering what lies at the edge, the place where space itself seems to vanish into infinity. Tonight, we journey past the limits of observation, where time slows, light bends, and the universe reveals its secrets. From the birth of galaxies to the silent expanse beyond the cosmic horizon, we explore what no human has truly seen. Welcome to Science After Dark, dear friends. If you enjoy these videos, be sure to leave a like and subscribe. It really means a lot to us. Now, let's get back to getting sleepy. Far beyond the warmth of our sun, beyond the familiar planets and the spiral arms of our Milky Way, the universe stretches into darkness so vast it defies comprehension. Each point of light we see in the night sky is not simply a star, but a beacon from the past, shining across unimaginable distances in time. When we gaze upwards, we are looking into history itself, tracing light that has traveled billions of years to reach us. It is a humbling reminder that our world is but a tiny island in a sea of cosmic wonder, and that the edge of the universe, the limits of what we can ever observe, lies far beyond the reach of our senses. Yet humanity has never stopped trying. From the earliest astronomers who traced the movements of planets with primitive tools, to the space telescopes orbiting high above our atmosphere, we have sought to map the infinite, to chart the unknowable. With each new discovery, we peer farther, capturing the faint glow of distant galaxies, mapping the cosmic web that threads through the void, and catching glimpses of light that existed before the Earth itself was born. The universe is not static, it is expanding, stretching the fabric of space and time, carrying galaxies ever outward, as if urging us to follow, to understand, to wonder. As we journey outward, we begin to confront the limits of perception. The edge of the observable universe is not a wall or a boundary in the ordinary sense. It is the horizon of light. Beyond it, regions exist that we cannot see, not because they are absent, but because their light has not had time to reach us. The cosmos whispers of infinity, teasing the human imagination with mysteries that may never be revealed. Here, the very rules of scale challenge the mind. Distances measured in billions of light years, stars so massive they dwarf our sun, galaxies colliding in silent, magnificent chaos over epochs longer than human history. And yet, within this vast emptiness, patterns emerge. Galaxies form intricate filaments, clusters gather like islands in an endless void, and dark matter, unseen but undeniable, weaves a hidden skeleton beneath the visible universe. Each discovery deepens the awe, reminding us that the universe is both orderly and chaotic, predictable and surprising. From the tiny flicker of a distant quasar to the sprawling cluster of galaxies spanning millions of light years, every structure tells a story of gravity, of time, of energy, and of beginnings that stretch back to the first moments of existence itself. To venture toward the edge of the universe is to step into a realm where light and time intertwine, where every photon carries the memory of ancient cosmic events, and where the mind is forced to confront the scale of infinity. It is a journey not only across space, but through the very history of reality, revealing the beauty, the mystery, and the fragility of all that exists. Here, at the outer limits of observation, we begin to feel both the enormity of the cosmos and the small, fleeting significance of our own place within it. This is the edge of the universe, a horizon that expands with every discovery, a boundary defined not by walls but by the limits of light, a frontier that inspires wonder, curiosity, and the endless drive to explore the unknown. And as we take our first steps into this infinite expanse, we are reminded that every star, every galaxy, every ripple of light carries with it a story waiting to be seen, understood, and imagined. As humans, we have always looked up, driven by a curiosity that refuses to be contained by our small world. At night, our ancestors traced the motions of stars, charted the passage of planets, and imagined what lay beyond the tiny patch of sky visible to them. Over centuries, our tools grew sharper, our vision clearer, and our understanding deeper. The telescope became a window into distant worlds. Satellites carried our gaze beyond the veil of Earth's atmosphere. Probes traveled to the edges of our solar system and sent back whispers of what lies farther still. Each discovery was a step, a bridge, a journey toward a horizon that moves ever outward. We call it the cosmic horizon, the limit of the observable universe, defined by the speed of light and the age of the cosmos. Every star, every galaxy we see, exists not as it is now, but as it was when its light began its long journey toward us. A galaxy a billion light years away shows us events from a billion years ago, frozen in light that has traveled across the void. Beyond this horizon, the universe may stretch infinitely, regions forever beyond our perception, carrying histories and structures that our instruments can never touch. And yet, even as we confront the limits of what can be seen, we continue to push outward, searching for patterns, signals, and truths hidden in the fabric of space and time. Through these efforts, humanity has learned to see not just the stars themselves, but the vast structures that bind them together. Galaxies cluster into massive filaments, separated by immense voids, forming a cosmic web that stretches across the sky. Invisible forces, like dark matter and dark energy, guide the dance of these structures, shaping a universe far more intricate than the naked eye could ever perceive. Every discovery reinforces both the magnificence and the mystery of existence, revealing how delicate yet relentless the forces of nature truly are. And yet, observing the universe is not merely a matter of measuring distances or cataloging galaxies. It is a meditation on time itself. The farther we look, the deeper we peer into the past. Light from the earliest galaxies reaches us faint and redshifted, stretched by the expansion of space, carrying a record of cosmic infancy. Through this light, we witness the birth of stars, the formation of galaxies, and the earliest flickers of energy that shape the cosmos. We are, in effect, archaeologists of the universe, excavating history encoded in photons that have traveled billions of years to reach our instruments. In chasing this light, we also confront the limits of our imagination. The universe is not a static canvas. It is expanding, accelerating, stretching space-time itself. Distances grow even as we measure them. Galaxies that appear within reach may already be moving beyond the bounds of what we can ever observe. The cosmic horizon is not a wall, but a reminder that the universe is dynamic, vast, and in some ways unknowable. And yet, this impossibility only fuels the human desire to explore, to model, to understand what lies beyond our senses. As we continue this journey toward the edge, we begin to see the universe not as a collection of isolated stars and galaxies, but as a vast interconnected network bound by forces that defy intuition. Gravity sculpts the cosmic web, dark energy accelerates its expansion, and time weaves its invisible thread through every event, every collision, every burst of light. We begin to realize that observing the universe is not merely an act of seeing, it is an act of understanding, of tracing the delicate interplay of matter, energy, and time across the grandest scales imaginable. And so, standing at the brink of what we can observe, we are both humbled and inspired. We see the cosmic horizon not as a barrier, but as a doorway, a threshold that separates the known from the unknown, the visible from the invisible. Each galaxy, each cluster, each faint glow of ancient light is a testament to the universe's vastness and to humanity's unyielding curiosity. As we chase this light and probe this horizon, we step closer to understanding the structure, history, and ultimate fate of everything that exists. The farther we look into space, the farther back in time we travel. This is not metaphor, it is literal. Light has a finite speed, and when we observe a galaxy billions of light years away, we are seeing it as it existed billions of years ago. In this sense, every telescope is a time machine, and every image of the deep sky is a snapshot of the ancient universe. But as we approach the extreme limits of observation, something strange begins to happen. The light becomes faint, it stretches, it reddens. This phenomenon, known as redshift, occurs because the universe itself is expanding. Space is not empty and static, it is dynamic, stretching like an invisible fabric. As space expands, it pulls light along with it, stretching its wavelength. The farther light travels, the more it is stretched, shifting toward the red end of the spectrum. At extreme distances, this stretching becomes so severe that visible light transforms into infrared, then microwave radiation. Galaxies at the edge of observation no longer shine like bright spirals or glowing clusters. They fade into whispers of radiation, barely distinguishable from cosmic noise. And beyond a certain distance, something even more profound happens. There are regions of space moving away from us faster than the speed of light. This does not violate physics, because nothing is moving through space faster than light. Instead, space itself is expanding. The fabric between galaxies stretches so rapidly that their light will never reach us. Not now, not ever. This is the true cosmic boundary. It is not a wall. It is not an edge you could collide with. It is a horizon defined by time and expansion. Beyond it, galaxies may exist in numbers beyond imagination. Entire clusters may be forming, colliding, evolving, but their light is forever cut off from us. They are causally disconnected from our reality. To us, they are unreachable, unknowable. And yet, even at this boundary, we detect something ancient. A faint glow that fills the entire universe. The cosmic microwave background. This radiation is the afterglow of the Big Bang, the oldest light we can see. It does not come from a single direction or a single source. It surrounds us. It is everywhere. It is the thermal echo of a universe that was once dense, hot, and nearly uniform. When we observe this background radiation, we are looking back over 13 billion years, to a time when galaxies did not yet exist, when stars had not yet formed, when the universe was still in its infancy. This is as close to the beginning as light allows us to see. But even this ancient glow is not the beginning itself. Before this moment, the universe was opaque, a dense plasma where light could not travel freely. There exists a barrier in time, not just space. A moment before which we cannot see because photons were trapped, scattered endlessly in a cosmic fog. So as we approach the edge of the universe, we encounter not only a spatial horizon, but a temporal one. A limit to vision, a limit to knowledge, a limit imposed not by technology, but by the nature of reality. And this realization changes everything. The edge of the universe is not simply far away, it is embedded in time itself. It reminds us that our understanding is bounded by physics, that there are epochs forever hidden behind cosmic curtains, and regions permanently beyond our observational reach. Yet paradoxically, this boundary is also a triumph, because even knowing that it exists means we have measured it, calculated it, understood its shape and behavior. We have traced the expansion of space, mapped the afterglow of creation, and determined the size of the observable cosmos to astonishing precision. We stand at the shoreline of infinity, not because we have traveled there physically, but because we have followed light as far as it can possibly go. And beyond that horizon, beyond the fading galaxies and the ancient microwave glow, lies a question that has haunted cosmologists for decades. If we cannot see beyond the observable universe, what is really there? We have reached the observable limit of the universe. We have followed light backward through billions of years, mapped the afterglow of creation, and traced the expansion of space to its measurable boundary. But the most unsettling realization is this: the observable universe is not the whole universe. It is only the part we can see, and what lies beyond it may be far larger than anything our minds are prepared to accept. The observable universe spans roughly 93 billion light-years in diameter. That number alone feels impossible. And yet, this vast cosmic sphere is only a bubble defined by the distance light has traveled since the beginning of time. It is not the edge of existence. It is merely the edge of our perception. Beyond it, space almost certainly continues. Current cosmological models suggest that the universe, on large scales, appears flat, not curved inward like a sphere, not curved outward like a saddle, flat. And if the universe is truly flat, then the simplest explanation is that it extends infinitely, or at least so far that its true size dwarfs the observable portion beyond comprehension. Imagine standing on a shoreline at night, holding a lantern. The light illuminates a small circle of sand around you. Beyond that circle lies darkness. But the darkness is not emptiness. It is simply beyond the reach of your light. The observable universe is that circle. Beyond it could be trillions upon trillions of galaxies structured into cosmic webs, forming clusters, birthing stars, collapsing into black holes, all unfolding in regions forever separated from us by expansion. And expansion is the key. The universe is not only expanding, it is accelerating. Dark energy, a force we still do not fully understand, drives galaxies apart at increasing speed. Over time, more and more of the universe will cross the cosmic horizon. Light that could have reached us today may never reach future observers. The universe, from any given vantage point, is slowly isolating itself. In the far future, distant galaxies will vanish from view entirely. Astronomers trillions of years from now, if such beings exist, may look into the sky and see only their local galaxy, unaware that a vast cosmic web once filled the darkness. In this sense, we are living in a privileged era. We exist at a time when the universe is still visible. But even beyond expansion, there is a deeper question, one that reshapes how we think about reality itself. What happened in the first fraction of a second after the Big Bang? The theory of cosmic inflation proposes that the universe underwent an explosive expansion almost immediately after its birth, expanding faster than the speed of light in an unimaginably brief moment. During this phase, space itself stretched exponentially, smoothing out irregularities and creating the large-scale structure we observe today. If inflation is correct, then our observable universe may be just one region where inflation stopped. Beyond our horizon, inflation may have continued spawning other regions of space, other bubbles, each potentially with different physical conditions. This is where cosmology brushes against something extraordinary. The multiverse hypothesis, not in a science fiction sense of alternate Earths and parallel selves, but as a natural consequence of inflationary physics. If inflation is eternal in some regions, then the universe as a whole could be a vast, endlessly generating landscape of cosmic domains, each with its own expansion history, its own structure, perhaps even its own physical constants. We cannot observe these regions directly. They are separated from us not by distance alone, but by the relentless expansion of space. Yet the mathematics that describe inflation allow for this possibility. And if true, it would mean that what we call the universe is only a fragment of a far grander structure. But even without invoking inflation or multiverse scenarios, the sheer scale beyond our horizon is staggering. If space is infinite, then patterns repeat. Given enough distance, configurations of matter would statistically recur. Somewhere, impossibly far away, there could exist galaxies nearly identical to ours. Stars arranged in familiar patterns, perhaps even worlds that resemble Earth, not because of destiny or design, but because infinity allows repetition. And yet, this idea is deeply unsettling, because it forces us to confront how small our observable region truly is. Every civilization that has ever risen and fallen, every ocean that has formed, every mountain range that has eroded, every thought ever conceived, all of it exists within a cosmic bubble that may be a microscopic fragment of a far greater reality. And still, we cannot see beyond it. There is no telescope powerful enough, no signal fast enough, no probe capable of crossing the expanding gulf. The edge of the observable universe is not a technological limitation, it is a fundamental boundary written into the laws of physics. But here is the paradox. Even though we cannot see beyond the horizon, the structure we observe inside it carries clues about what lies outside. The uniformity of the cosmic microwave background, the flatness of space, the distribution of galaxies. These are fingerprints of processes that occurred when the universe was far smaller, when regions now separated by billions of light years were once intimately connected. In this way, the universe leaves us hints, subtle imprints of a larger story. We may never step beyond the cosmic horizon, but through theory, mathematics, and observation, we can sketch its possible shape. And what emerges is a picture not of a small, self-contained cosmos, but of a reality that may be vastly larger, perhaps infinite, perhaps eternally generating new regions of space. The edge, then, is not an end. It is a perspective, a limit imposed by time and expansion, not by existence itself. Beyond it, the universe likely continues silent, unreachable, magnificent, expanding into a darkness that is not empty, but simply beyond our light. And perhaps the most profound realization of all is this: the true size of reality may forever exceed our ability to witness it, yet we understand enough to know that it does. And that knowledge alone changes how we see everything. The universe is not only vast, it is temporary. Everything we have seen, galaxies, stars, planets, nebulae, exists within a cosmic timeline that is slowly unfolding toward an ending. Not an explosion, not a collapse, but a fading. The expansion of the universe is accelerating. Dark energy continues to push galaxies apart, stretching space at an ever-increasing rate. Over billions of years, distant galaxies will slip beyond the cosmic horizon, their light redshifted into darkness, their existence forever inaccessible. The night sky will change. Constellations will distort. Neighboring galaxies will vanish. The great cosmic web will thin from view until only our local group of galaxies remains gravitationally bound together. Eventually, even that will change. Stars do not burn forever. They consume hydrogen, fuse helium, create heavier elements, and slowly exhaust their fuel. Massive stars die violently, exploding in supernovae. Smaller stars fade into white dwarfs. Over trillions of years, star formation itself will slow as galaxies run out of cold gas. The universe will enter what cosmologists call the stelliferous era's end. No new stars, no brilliant nebulae, only aging stellar remnants drifting through increasingly empty space. But time does not stop. Trillions upon trillions of years pass. White dwarfs cool into black dwarfs. Neutron stars collide or decay. Black holes, the most durable structures in existence, dominate the cosmos. Galaxies become graveyards of faint remnants orbiting invisible singularities. And yet, even black holes are not eternal. Through a process known as Hawking radiation, they slowly lose mass, emitting faint particles over unimaginable spans of time. For stellar mass black holes, this evaporation would take far longer than the current age of the universe, but given enough time, even they disappear. In roughly 10 to the power of 100 years, a number so vast it defies intuition, the last black holes evaporate. The final anchors of structure are gone. What remains is darkness. Not dramatic darkness, not violent emptiness, but a thin, cold, dilute sea of particles, electrons, photons, neutrinos, spread across an ever-expanding void. This is the heat death of the universe, a state of maximum entropy. No gradients, no structure, no usable energy. Physics continues, but nothing meaningful happens. No stars ignite, no galaxies form, no complexity rises. The universe becomes a quiet equilibrium, a fading echo of everything it once was. And here is the profound truth. This fate is not speculative fantasy. It emerges naturally from our current understanding of thermodynamics, expansion, and cosmology. If dark energy remains constant, if expansion continues accelerating, then isolation and entropy are inevitable. The edge of the universe is not only spatial, it is temporal. There is a horizon in the future just as there is one in space, a limit beyond which no light will ever return, no interaction will ever reconnect distant regions again. The cosmos is slowly isolating itself, but there is something extraordinary about this moment. Right now, the universe is alive with structure. Stars are forming, galaxies are colliding, planets are cooling, life is thinking. We exist in a narrow window between chaos and silence. Too early, and the universe was a plasma inferno. Too late, and it becomes a frozen expanse of fading particles. We live in the brief era where complexity is possible. And within that brief window, consciousness has emerged, capable of looking outward, and understanding the arc of cosmic history from beginning to end. That may be the most astonishing fact of all. Atoms forged in ancient stars arranged themselves into minds that can comprehend stellar life cycles, cosmic expansion, black hole evaporation, and the eventual death of everything. The universe has become aware of itself. And even if, trillions upon trillions of years from now, the last light fades and the cosmos settles into cold equilibrium, there was once a time when it was illuminated not only by stars, but by understanding. The edge of the universe is not something we will ever physically reach. It is a boundary defined by light, time, and expansion. But in tracing its limits and mapping its beginning and predicting its end, we have already touched it in the only way that truly matters. Through knowledge, through curiosity, through the relentless human drive to look into the darkness and ask what lies beyond. And in that act alone, the universe is no longer silent. It is a story. And for a brief moment in eternity, we are here to tell it. But if we are to understand the edge of the universe, we cannot only look outward, we must go backward. All the way back, not to the first stars, not to the first atoms, but to the first fraction of a second. Roughly 13.8 billion years ago, the universe existed in a state so extreme that the word fire does not begin to describe it. Temperature was not thousands of degrees, not millions, not billions. It was trillions upon trillions of degrees. Matter as we know it did not exist. There were no atoms, no nuclei, no protons or neutrons. Only energy compressed into an unimaginably dense state. In the first 10 to the power of -43 seconds, the Planck epoch physics as we understand it breaks down. Gravity, electromagnetism, the strong and weak nuclear forces may have been unified. We do not yet possess a theory of quantum gravity capable of describing this era. This is the true frontier of cosmology. Plus, then something happened. Inflation. In less than a trillionth of a second, space expanded exponentially faster than light, not through motion, but through expansion of space itself. A region smaller than a proton expanded to astronomical size almost instantly. This single event explains why the universe appears flat, why distant regions share the same temperature, why structure exists at all. Tiny quantum fluctuations, microscopic irregularities in the fabric of space were stretched to cosmic scales. These fluctuations became density variations. Those variations became gravity wells, and gravity wells became galaxies. Everything you see, every galaxy cluster, every star, every planet, originated from quantum noise amplified by inflation. The universe's large-scale structure began as microscopic randomness. After inflation ended, the universe was still unimaginably hot. Quarks condensed into protons and neutrons. Within minutes, nuclear fusion created the first light elements: hydrogen, helium, trace amounts of lithium. This period is known as Big Bang nucleosynthesis. For hundreds of thousands of years afterward, the universe remained a glowing plasma. Photons scattered constantly off charged particles, unable to travel freely. Then, about 380,000 years after the beginning, something profound occurred. The universe cooled enough for electrons to combine with nuclei. Atoms formed. Light was finally able to move without constant scattering. The cosmos became transparent. That ancient light is what we now detect as the cosmic microwave background, a faint, nearly uniform radiation filling all of space. When we observe it, we are seeing the universe as it was when it was only 380,000 years old. This is not theory without evidence. Satellites like the Planck mission and the Wilkinson Microwave Anisotropy Probe have mapped this radiation with extraordinary precision, revealing tiny temperature fluctuations, variations of 1 part in 100,000. Those tiny fluctuations are the seeds of everything. From them, gravity slowly amplified structure. Over millions of years, hydrogen clouds collapsed. The first stars ignited. Ultraviolet light flooded the cosmos. Galaxies assembled. Black holes formed at their centers. The universe transitioned from darkness to structure, from simplicity to complexity, and all of it was encoded in those first seconds. When we talk about the edge of the universe, we often imagine distance. But the deeper truth is this: the edge is also a memory, a fossil imprint of the earliest moments. Every galaxy we observe carries the fingerprint of inflation. Every structure traces back to quantum fluctuations. Every atom in your body was once part of that primordial fire. The edge of the universe is not just far away, it is behind us in time. And the closer we get to understanding those first moments, the closer we approach the true boundary of physics itself, the point where our equations fail and new laws must take their place. That is where the next frontier lies. Not merely at the edge of space, but at the edge of understanding. As we peer deeper into the cosmos, we quickly realize that the universe we see is only part of the story. Galaxies spin, clusters collide, and stars orbit around centers that seem almost empty. And yet, the motions defy expectations. According to the visible matter alone, galaxies should fly apart. Stars at the edges should escape, leaving nothing behind. But they do not. Something unseen holds them together, a hidden presence that exerts gravitational influence without emitting a single photon. This is dark matter, the invisible skeleton of the cosmos. Though we cannot see it directly, its fingerprints are everywhere. Gravitational lensing bends the light of distant galaxies, creating arcs and distortions in ways that visible matter alone cannot explain. Clusters of galaxies reveal mass far beyond what telescopes can detect, and computer simulations of cosmic structure, run with and without dark matter, show dramatically different results. Only with dark matter do filaments form, galaxies cluster, and the vast web-like structure of the universe emerge naturally. It is a silent architect, shaping the cosmos over billions of years, guiding the formation of the stars, galaxies, and clusters we now observe. Theories abound about its nature. Some propose it consists of weakly interacting massive particles, WIMPs, that pass through ordinary matter undetected. Others suggest axions, hypothetical particles with unique properties. Entire underground laboratories and deep space experiments search relentlessly for evidence, attempting to capture even a whisper of interaction. Yet so far, the substance remains elusive, a mystery that challenges the limits of physics. Dark matter dominates the mass of the universe, outweighing the ordinary atoms we are made of by roughly 5 to 1, and yet it is completely invisible to our senses. Its presence, however, has profound consequences for understanding the universe's edge. Dark matter not only governs the dynamics of individual galaxies, but also shapes the largest cosmic structures. The cosmic web, the vast network of filaments stretching across billions of light years, is woven primarily by dark matter. Galaxies trace these invisible threads, clustering along them and leaving enormous voids in between. When we contemplate the edge of the observable universe, we are not merely thinking about distant stars and galaxies, we are contemplating a vast framework of unseen matter that defines the very shape of reality. And there is something poetic about this invisible scaffold. It reminds us that the universe is stranger than intuition allows. What we see, every brilliant star, every swirling nebula, is merely the luminous tip of a vast, hidden structure. The edge of the universe, then, is not just a boundary of distance, but a boundary of perception. Beyond the light, beyond the stars, the true architecture of the cosmos is largely invisible, quietly dictating the motion and evolution of everything within it. Even more intriguingly, dark matter may hold clues to the universe's ultimate fate. Its gravitational pull slows the expansion locally, binding galaxies and clusters together. But as dark energy continues to accelerate the universe's expansion on the largest scales, a delicate interplay unfolds. Structures held together by dark matter persist even as vast swaths of space recede beyond our horizon. In 1 trillion years, the visible universe may shrink to only what remains gravitationally bound islands of matter floating in an ever-expanding darkness. Dark matter will have determined what survives, what remains, and what fades from view forever. In studying dark matter, we confront the profound limits of human understanding. We can model it, infer its effects, and simulate its role in cosmic evolution, but we cannot touch it, taste it, or see it directly. Yet even as an invisible substance, it shapes everything. It has determined the paths of stars, the shapes of galaxies, and the fate of clusters. It has written the universe's history without a word, leaving us only with clues, equations, and the faint pull that bends light and guides celestial motion. The edge of the universe is not just far away, it is built upon these invisible foundations, an architecture that exists beyond our senses but underlies all we perceive. And in this realization lies a kind of awe unlike any other. We are observers in a universe where most of the matter is hidden, where light illuminates only a fraction of reality, yet where the invisible threads dictate everything that lives, moves, and shines. The edge of the universe, therefore, is not a physical barrier, nor a wall of stars. It is a boundary of perception, a frontier of mystery, and a reminder that the cosmos is infinitely stranger, infinitely larger, and infinitely more intricate than our eyes, our instruments, or even our imagination might suggest. If dark matter is the invisible skeleton that holds the universe together, then dark energy is the unseen force that tears it apart. For decades, astronomers assumed that gravity would eventually slow the expansion of the universe. Stars, galaxies, and clusters were thought to drift outward more slowly over time, bound in a cosmic dance that might eventually halt or even reverse. But in the late 1990s, two independent teams studying distant supernovae discovered something extraordinary. The expansion of the universe is accelerating, not slowing, not steady, accelerating. The cosmos is not coasting. It is being stretched by a force we cannot see, a force we cannot touch, yet one that dominates the universe in both magnitude and mystery. This is dark energy, a term that, even in its name, hints at our ignorance. It makes up roughly 68% of all the energy in the cosmos, vastly outweighing the ordinary matter we see and the dark matter we infer. Unlike gravity, which pulls, dark energy pushes. It drives galaxies apart, increases the distance between clusters, and stretches space itself at an ever-growing rate. The farther 2 points are from each other, the faster they recede. This is not motion through space. It is the expansion of space itself, stretching the fabric of reality in all directions. The consequences of this accelerating expansion are profound. The universe we see today, filled with billions of galaxies, is only temporary in its current form. As time moves forward, more and more galaxies will recede beyond the cosmic horizon. Light that could have reached us yesterday may never reach us tomorrow. Future civilizations, looking out into the cosmos, may witness a sky that appears almost empty, isolated, and dark. The grandeur of the cosmic web, the brilliant tapestry of galaxies, clusters, and filaments will fade into the unseen, leaving only a few gravitationally bound islands of matter. Yet even as dark energy isolates the universe, it reveals something fundamental about reality, that space itself is dynamic. Space is not a passive backdrop where matter simply exists. It is an active participant in cosmic evolution, expanding, stretching, and shaping everything we observe. The universe is alive, not biologically, but physically, its structure and behavior constantly evolving under forces we are only beginning to understand. The edge of the universe, therefore, is not simply a place of distance. It is a horizon defined by expansion, by the relentless pull of dark energy, and by the fundamental interplay between matter, energy, and space-time itself. Theoretical physicists speculate endlessly about the nature of dark energy. Is it a constant, inherent property of space, the cosmological constant that Einstein once proposed? Or is it dynamic, changing over time, a field that waxes and wanes as the universe evolves? Could it be evidence of entirely new physics, beyond the standard model, hinting at dimensions, fields, or forces we have yet to imagine? Every answer deepens the mystery, forcing us to confront how little we truly know about the universe we inhabit. But in understanding dark energy, we also glimpse the fate of everything. Galaxies that are not gravitationally bound will drift apart, stars will die, black holes will evaporate. The universe will expand into near-perfect isolation, a vast, cold, dark emptiness. And yet, this fate is not sudden. It unfolds over unimaginable spans of time, giving rise to a cosmic story of motion, change, and inevitability. Dark energy is both destroyer and storyteller, stretching the canvas on which the universe paints its narrative, guiding the evolution of matter, energy, and light across billions upon billions of years. In studying dark energy, we confront one of the greatest paradoxes of existence. The universe is finite in the light we can observe, yet vast beyond imagination. It is structured and orderly, yet dominated by invisible forces. It is comprehensible enough for us to map and model, yet mysterious enough to remind us of our own limitations. The edge of the universe, shaped by this hidden energy, is no longer a distant boundary. It is a dynamic, evolving frontier, a reminder that space, time, and matter are not static, but entwined in a cosmic story we are only beginning to understand. And so, as we gaze toward the edge, we see not emptiness, but the power that drives everything apart. Dark energy defines the horizon, shapes the future, and challenges our understanding of what it means to inhabit a universe that is alive, expanding, and inexorably moving toward the unknown. It is a force both terrifying and magnificent, silent and omnipresent, a cosmic hand stretching the fabric of reality in ways our minds can barely comprehend. Among the most enigmatic and powerful structures in the universe, black holes represent both an end and a beginning. They are born from death, the collapse of massive stars, yet their influence stretches across billions of years, shaping galaxies and even the evolution of the universe itself. A black hole is a region where gravity has become so intense that not even light can escape. The boundary, the event horizon, marks the point of no return. Once crossed, all matter and information is trapped, its fate sealed by the laws of physics. Yet black holes are not merely destructive, they are engines of cosmic evolution. Supermassive black holes, millions to billions of times the mass of our Sun, sit at the centers of galaxies, anchoring the stars around them. They regulate star formation, influence galactic collisions, and even drive powerful jets that can extend across thousands of light years. In this sense, black holes are architects as much as they are destroyers, hidden rulers of the cosmic landscape, invisible yet dominant. Their formation begins with gravity's unyielding pull. When a massive star exhausts its nuclear fuel, its core collapses under its own weight. Electrons and protons are crushed together, producing a singularity, a point of infinite density surrounded by an event horizon. Around it, space and time themselves warp in ways that challenge human intuition. Time slows near the horizon. Light bends, stretched and twisted by gravity. For a distant observer, infalling matter seems to freeze at the edge, while for the matter itself, the fall is immediate and irreversible. But the story of black holes does not end with collapse. In the 1970s, Stephen Hawking proposed that black holes are not entirely black. Quantum effects near the event horizon produce faint radiation, allowing them to slowly evaporate over unimaginable spans of time. Even the most massive black holes, once thought eternal, are not permanent. Their eventual evaporation is one of the final chapters in the long-term evolution of the universe, leaving behind nothing but energy diffused across the cosmos. Black holes also challenge our understanding of information. What happens to the details of matter that falls in? Are they lost forever, or somehow encoded on the horizon itself? This paradox has become a central question in theoretical physics, linking gravity, quantum mechanics, and the nature of reality itself. Some propose that the information is preserved holographically on the surface of the event horizon. Others suggest exotic possibilities in higher dimensional space or connections to parallel universes. Each theory stretches our minds as far as the universe itself stretches our senses. The most mysterious black holes of all are the supermassive giants. At the centers of galaxies, these behemoths influence everything around them. The Milky Way's own central black hole, Sagittarius A, has a mass of 4 million suns, yet its presence is largely invisible except for the subtle dance of stars orbiting it. Observations with telescopes like the Event Horizon Telescope have even allowed humanity to capture the first images of a black hole's shadow, giving a glimpse of what was once purely theoretical. For the first time, we have seen the silhouette of a singularity, a cosmic heart that shapes entire galaxies. Black holes are also cosmic laboratories. In their extreme gravity, time dilates, space curves, and light bends conditions impossible to replicate on Earth. They allow physicists to test general relativity, probe quantum effects, and imagine conditions in the first moments of the universe. Every observation, every simulation, every equation brings us closer to understanding not just black holes, but the underlying laws that govern the cosmos. And yet, for all we know, black holes are far more common and far stranger than we can see. Stellar mass black holes may number in the hundreds of millions in our galaxy alone, invisible except for the occasional flare as they consume nearby matter. There may even be primordial black holes relics from the earliest fractions of a second after the Big Bang, tiny yet dense, wandering silently through space. Some could even account for portions of dark matter, hidden architects we have yet to fully understand. In contemplating black holes, we confront a paradox of power and invisibility. They are the universe's ultimate destroyers, yet they shape creation itself. They exist at the edges of understanding, where physics and imagination meet, where time and space behave in ways that challenge perception. And in the context of the universe's edge, black holes are markers, reminders that the cosmos is not merely vast and expanding, but also violent, extreme, and beautiful in ways that test the limits of comprehension. When we talk about the universe, we often imagine it as a vast, empty expanse, stretching infinitely in all directions. Yet cosmologists know that the universe has a shape, a geometry, and understanding it is essential to knowing what lies at its edge. Space is not merely a passive stage where matter and energy perform. It is dynamic, curved, and intertwined with time itself. The shape of space determines how light travels, how galaxies cluster, and how the cosmos will evolve over trillions of years. Observations of the cosmic microwave background, combined with precise measurements of supernovae and galaxy distributions, suggest that the universe is astonishingly flat. Not flat in the sense of a tabletop, but flat in terms of curvature. Over the largest scales we can measure, the angles of triangles add up as in Euclidean geometry. Light travels in straight lines, and parallel lines remain parallel. This flatness implies that the universe is either infinite or so vast that its curvature is undetectable across the observable horizon. Yet flatness is only part of the story. Cosmologists also explore topology, the global shape of space. Even a flat universe could be finite, wrapping around itself like a three-dimensional torus, where traveling in one direction long enough might bring you back to your starting point. Alternatively, the universe could be infinite, extending without end, a cosmic plane of boundless galaxies and dark voids. The difference is profound. In a finite universe, every possible arrangement of matter could, in theory, repeat somewhere else. In an infinite universe, the repetitions are inevitable, stretching the imagination to realms we can barely conceive. Curvature, topology, and geometry are not abstract concepts. They influence the very fate of the cosmos. A positively curved universe, like a four-dimensional sphere, might eventually stop expanding and collapse. A negatively curved universe, saddle-shaped, would expand forever, but with ever-increasing isolation. Flatness, as observations suggest, implies expansion will continue indefinitely, with distant galaxies disappearing beyond our horizon, leaving only local clusters behind. Geometry, then, is destiny. The shape of space dictates not only how the universe looks, but how it will evolve across unimaginable spans of time. The concept of geometry also ties directly to cosmic inflation. During the first fraction of a second after the Big Bang, inflation smoothed out any initial irregularities, stretching space so rapidly that any curvature became negligible. Inflation predicts that the universe should appear flat, and modern observations confirm this with remarkable precision. This connection between the earliest moments of time and the largest scales of space underscores a profound truth. To understand the edge of the universe, we must understand both its beginning and its global structure. Mathematical models also suggest other exotic possibilities. The universe could be finite but unbounded, a higher dimensional analog of a Mobius strip or a three-dimensional torus, where traveling in a straight line eventually returns you to your starting point. Light paths in such a universe could circle back, creating patterns in the cosmic microwave background detectable as subtle repetitions across the sky. Scientists search for these signatures, hoping to glimpse evidence of the universe's true shape. Each measurement, each observation, adds another brushstroke to a cosmic portrait far beyond our senses. Even if we cannot determine the universe's ultimate extent, studying its geometry brings us closer to understanding the edge. It allows us to define horizons, predict the behavior of galaxies, and model the universe's long-term fate. Geometry gives structure to the chaos, a framework on which the vast, expanding cosmos unfolds. It is both elegant and humbling, a reminder that the universe operates according to principles far more subtle than mere observation can reveal. And perhaps the most astonishing realization is this: every atom in your body, every star in the night sky, every galaxy exists within a vast structure whose shape, curvature, and topology influence every motion, every trajectory, every interaction. The edge of the universe is not just a distance, not just a horizon of light. It is defined by the underlying geometry of reality itself. In contemplating this, we confront not only the scale of existence, but the deep, intrinsic rules that govern everything we see and everything we cannot see. One of the most profound questions in cosmology is deceptively simple. How big is the universe? Is it finite, with boundaries we may never reach? Or is it infinite, stretching endlessly in every direction? The answer is not obvious and may ultimately be unknowable. Our observable universe, the sphere around us limited by the speed of light and the age of the cosmos, is vast, roughly 93 billion light-years across. Yet, this is only what we can see. Beyond it lies a realm that may extend without end, a domain forever beyond our instruments, beyond our perception. If the universe is finite, it must have a shape that is unbounded. That is, you could travel in one direction and, eventually, return to your starting point. Imagine a three-dimensional analog of a video game world that loops seamlessly. Light traveling in such a universe could circle back, creating multiple images of the same object in the sky. Scientists have searched for such repeating patterns in the cosmic microwave background, looking for clues that might reveal the universe's true limits. So far, evidence suggests flatness, but the question remains open. Even in a flat universe, finite structures could exist in ways that challenge intuition. Infinity, on the other hand, is even more difficult to grasp. In an infinite universe, every possible arrangement of matter is not just conceivable, it is inevitable. Galaxies, stars, and perhaps even planets nearly identical to Earth could exist, repeated across unimaginable distances. Every possible configuration of atoms, every sequence of events, could occur somewhere in the cosmos. Infinity is not merely vastness, it is repetition, probability, and scale beyond comprehension. The very concept challenges human imagination, forcing us to consider that the universe may extend without boundaries, without end, with patterns that repeat in ways our minds can barely visualize. The question of finitude also intertwines with inflation and the multiverse. Cosmic inflation predicts that while our observable universe appears flat, other regions of space could have inflated independently, creating bubble universes with their own physical laws, constants, and histories. In this view, what we call the universe is just one of countless domains within a greater cosmic landscape. These other regions may be forever beyond our observational reach, separated from us by the relentless expansion of space. If this is true, then the universe is not only infinite in space, but layered with realities we cannot perceive. Yet even without invoking a multiverse, the consequences of infinity or finitude are profound. In a finite universe, gravity, expansion, and dark energy define what structures can exist and how long they last. Galaxies are limited in their interactions, and the horizon defines what we can ever know. In an infinite universe, the rules of probability dominate. Unlikely events occur somewhere else, and the concept of uniqueness loses meaning. The universe may contain infinite repetitions of every pattern, every configuration, and every event. To consider infinity is to confront the limits of both physics and philosophy, to face a reality that is not just large, but unimaginably vast. For humans, this realization is both humbling and liberating. It reminds us that while we are small in space, small in time, and small in perspective, we have the capacity to observe, theorize, and imagine realities far beyond our immediate experience. The universe finite, infinite, or multiversal challenges the human mind to expand alongside it, to think in scales that defy intuition, and to seek understanding in a cosmos that may never fully reveal itself. In contemplating the edge, the horizon, the limits of observation, we begin to understand a truth. The universe is defined not just by what we see, but by what we cannot see. Its boundaries, whether finite or infinite, are written in the fabric of space, the rules of physics, and the expansion of time. The edge is simultaneously near and far, known and unknowable, a concept as much philosophical as scientific. And in this tension between understanding and mystery lies the wonder of existence, the profound realization that the universe is far grander, stranger, and more beautiful than we could ever imagine. The universe we see today, alive with stars and galaxies, is only a fleeting moment in cosmic time. Billions of years from now, the cosmos will look profoundly different, and yet its transformation will be dictated by the same forces we observe today: gravity, dark matter, dark energy, and the relentless expansion of space. To understand the edge of the universe is to understand not only its vastness, but its destiny. In the next few billion years, our own Milky Way will collide with the neighboring Andromeda galaxy. Stars will pass near one another in a chaotic ballet, gravitationally perturbed, yet rarely colliding. Galaxies will merge, forming vast elliptical structures, their spiral arms twisted and rearranged. The night sky of any observers at that time will be unrecognizable, transformed into a swirling maelstrom of stars, dust, and light, a cosmic dance unlike anything we can witness today. As the universe continues to expand, galaxies beyond our local group will drift farther away, receding faster than the speed of light due to the acceleration caused by dark energy. Eventually, trillions of years from now, these galaxies will vanish from view, leaving only the bound structures that remain gravitationally connected. The cosmos will become a series of isolated islands, each a solitary cluster of stars and remnants, drifting in an ever-growing sea of darkness. Stars themselves will not burn forever. The universe will enter what astronomers call the stelliferous era's decline. Smaller, long-lived stars, red dwarfs, will continue to shine for trillions of years, their faint light the last remnants of stellar activity. Massive stars, already short-lived, will have long since expired, leaving behind white dwarfs, neutron stars, and black holes. Star formation will slow and eventually cease entirely as the supply of cold gas runs out, leaving the universe increasingly dark and quiescent. Over even longer timescales, white dwarfs will cool into black dwarfs, slowly fading into near invisibility. Neutron stars may collide or decay. Black holes, those eternal anchors of gravity, will dominate the landscape, yet even they are not immortal. Through the mysterious process of Hawking radiation, black holes slowly evaporate over unimaginably vast spans of time, emitting tiny amounts of energy until the final singularity disappears, leaving nothing behind. In this distant future, the universe will become a landscape of diffuse particles and fading radiation, an almost perfect equilibrium of entropy. This is the era of heat death, a state of maximum entropy where no useful energy remains, where all structure has dissolved, and where complexity ceases. The cosmos will no longer teem with stars, galaxies, or life. Even photons will be stretched into undetectable wavelengths, and the universe itself will become a dark, cold, dilute expanse. In this ultimate silence, the edge of the universe is no longer a distant horizon. It is the infinite, barren expanse of time itself, stretching endlessly without interaction, without growth, without change. Yet even in this desolate future, there is a paradoxical beauty. The universe's death is not sudden. It is the result of billions of trillions of years of evolution, a story written across unimaginable stretches of space and time. Every star that ever burned, every galaxy that ever formed, every black hole that ever devoured has contributed to the cosmic narrative. The universe's final state is not chaotic. It is a sublime equilibrium, the endpoint of laws we have come to understand, governed by gravity, thermodynamics, and the relentless flow of time. And in contemplating this future, we confront something profoundly human. The cosmos may fade, stars may die, and galaxies may vanish, yet for a brief instant, consciousness arises. Life, intelligence, and awareness exist in the fleeting window between creation and entropy. We are here, now, able to observe, measure, and imagine the vastness and fate of the universe. In doing so, we participate in the story of the cosmos, a story that stretches across billions of years and trillions of light years, a story that began with a singularity and will end in darkness, yet which is illuminated by understanding, curiosity, and imagination. The far future is also a meditation on scale. Time becomes incomprehensible. Numbers like 10 to the power of 100 years or more are not merely large, they are beyond intuition. The universe evolves in epochs beyond counting: the degenerate era, the black hole era, the dark era. Each phase represents the slow dissolution of structure, the fading of energy gradients, and the march toward maximum entropy. In this context, life, stars, and even galaxies are temporary actors in an eternal drama, their presence a fleeting, delicate anomaly in an otherwise cold and expanding cosmos. Yet even as we contemplate the heat death, the universe leaves traces of its history. the cosmic microwave background persists as a whisper of the Big Bang. The remnants of stars and black holes carry the chemical signatures of their formation. The large-scale structure, though largely dissolved, leaves subtle imprints. These traces are the universe's memory, the evidence of all that has been encoded in particles, radiation, and the very fabric of spacetime. The edge of the universe, in this ultimate sense, is not merely a distance or horizon, but the boundary of observability across time, the limit imposed by physics itself. And perhaps the most profound realization of all is this: the universe, vast and ancient, may eventually become silent, empty, and cold. Yet it is precisely during its brief, luminous era that understanding emerges. Consciousness arises, questions are asked, and the cosmos becomes aware of itself through observation. Stars, galaxies, black holes, and even dark matter and dark energy all contribute to a narrative that culminates not only in physical processes, but in awareness, in thought, in comprehension. The edge of the universe, then, is not simply a horizon in space, it is the frontier of knowledge, imagination, and human curiosity, a reminder that even in an impermanent cosmos, awareness allows the universe to know itself. As we step back from the vast scales of space and time, the universe begins to feel not only immense, but intimate. We have traced its birth, its expansion, its invisible scaffolding of dark matter, the relentless pull of dark energy, the monstrous gravity of black holes, and the eventual fading of all light. And yet, in contemplating these cosmic truths, a profound perspective emerges, one that reshapes not just how we see the universe, but how we see ourselves. The first reflection is humility. To stand at the edge of the observable universe is to confront the limits of human perception. Every galaxy, every star, every particle we observe is but a fraction of what exists. The universe dwarfs us in scale and time. Our lives, our civilizations, our fleeting histories, they are ephemeral against the backdrop of billions of years and trillions of light years. And yet, the very act of observing, of understanding, grants us significance. Though small, we are capable of grasping truths that stretch across time and space, bridging gaps that seem unbridgeable. The second reflection is wonder. The cosmos is not simply a collection of matter and energy, it is a narrative of emergence, structure, and complexity. From the initial quantum fluctuations that seeded galaxies to the delicate balance of forces allowing stars and planets to form, the universe unfolds in patterns of extraordinary beauty. Dark matter and dark energy, black holes and neutron stars, expanding space and cosmic horizons, all contribute to a universe that is simultaneously comprehensible and mysterious. To witness this is to experience awe, to recognize the extraordinary elegance of reality itself. Third is perspective. The universe teaches us about scale and temporality in ways no other discipline can. A single human life spans mere decades, yet the cosmos unfolds over billions of years. Civilizations rise and fall, stars are born and die, galaxies collide and vanish. Against this backdrop, our conflicts, ambitions, and anxieties seem small, yet our capacity to contemplate the cosmos is vast. We are brief, yes, but conscious, reflective, and curious traits that allow us to experience meaning in an otherwise indifferent universe. Fourth is resilience. In the face of cosmic impermanence, life persists. Complexity arises, patterns endure, and consciousness emerges, even if only for fleeting moments. We are part of a universe that is both fragile and enduring. Our existence is a testament to the rare and delicate conditions that allow complexity, intelligence, and curiosity to emerge. By studying the cosmos, by seeking knowledge of its edge, we affirm the persistence of awareness, even as the universe itself marches toward entropy. Finally, there is inspiration. The edge of the universe is not merely a physical horizon, but a metaphor for human potential. The cosmos challenges us to expand our minds, to ask questions that have no immediate answers, and to imagine realities beyond direct observation. It reminds us that knowledge, understanding, and imagination are the means by which we reach beyond ourselves, the tools that let a tiny, fragile species touch the infinite. To look into the universe is to confront both our smallness and our power, small in scale, yet capable of infinite thought. In this reflection, science and philosophy converge. The universe is vast, strange, and indifferent, yet it has given rise to beings capable of observing it, questioning it, and seeking meaning within it. The edge of the universe, the ultimate horizon, is both a physical boundary and an intellectual frontier. We cannot reach it with spacecraft, nor can we cross it with light. But we can reach it with ideas, understanding, and curiosity, traveling farther than any photon, venturing beyond the limits of matter into the limitless expanse of thought. And so, in contemplating the universe, we confront our own existence. We see both our insignificance and our uniqueness. We recognize that the cosmos is immense, ancient, and mostly unseen, yet within it, awareness has emerged. We are the universe reflecting on itself, conscious of its own history, capable of tracing its beginning, measuring its expansion, and imagining its ultimate fate. The edge of the universe is not only out there in space, it is also within us, the boundary of understanding, the horizon of curiosity, and the frontier of imagination. This reflection completes the cosmic journey. From the first sparks of the Big Bang to the ultimate silence of heat death, from the invisible scaffolding of dark matter to the accelerating push of dark energy, from black holes to infinite horizons, the universe has revealed itself as both a physical and philosophical frontier. And in observing it, in narrating it, in contemplating it, we participate in the most extraordinary phenomenon of all, consciousness within the cosmos. As our journey through the universe draws to a close, we are left with a sense of scale, time, and wonder that is difficult to grasp. We have traced the cosmos from its earliest fractions of a second to its farthest edges, explored the invisible forces that shape galaxies, and contemplated the ultimate fate of all matter and energy. We have ventured across billions of light years and trillions of years into the future, yet the story does not end with understanding alone. It ends with reflection on what it means to exist within such a vast, ancient, and enigmatic cosmos. The universe is immense. It is old, mysterious, and sometimes indifferent. Stars are born and die, galaxies collide and vanish, and black holes dominate their neighborhoods in silence. Dark matter structures the cosmos, while dark energy stretches it apart. Light itself has limits, and beyond our observable horizon lies a realm we may never see. Yet within this immensity, life and consciousness have emerged fragile, fleeting, and miraculous. We are here to witness, to observe, to ask questions, and to imagine what lies beyond. In a sense, the edge of the universe is not just a boundary in space or time. It is a boundary of perception, of understanding, and of curiosity. Every photon that reaches our telescopes, every signal that travels across the void, every calculation, observation, and theory brings us closer to that edge, not physically, but intellectually. We are explorers, not in ships, but in thought. Our minds traverse horizons that our bodies cannot, charting distances and epochs that defy comprehension. And perhaps that is the most extraordinary truth of all. The universe has given rise to beings capable of contemplating it. Consciousness has arisen within a cosmos of unimaginable scale. Through awareness, reflection, and curiosity, the universe has become aware of itself. Every discovery, every insight, every revelation is a small echo of this cosmic self-recognition. It is fleeting, yes, but profoundly meaningful. For a brief moment in the life of the universe, there is understanding, there is light, not just from stars, but from knowledge. As we look outward, we see galaxies drifting beyond view, cosmic filaments stretching into darkness, and stars burning their last hydrogen. As we look inward, we see ourselves tiny, ephemeral, yet conscious and inquisitive. The edge of the universe is both far away and within us, a horizon defined not by distance alone, but by imagination, reflection, and the unending drive to explore. And so, we close this chapter not with finality, but with possibility. The universe continues its expansion, dark energy continues to stretch space, and time marches inexorably toward the far future. Stars will fade, black holes will evaporate, and entropy will spread. Yet for now, for this moment in cosmic history, the universe is alive, vibrant, and comprehensible alive, not just in matter and energy, but in thought and curiosity. We have journeyed to the edge. We have traced its limits in space, in time, and in understanding. And though the ultimate horizon may never be reached, the journey itself has revealed something profound, that the universe, in all its vastness and mystery, has made room for awareness, reflection, and wonder. The cosmos is immense. We are small, but through curiosity, through science, and through imagination, we have touched the infinite.